So now that we've talked about the structure and functionality and motivation for the state pattern, let's go ahead and take a look at its implementation in C++. So we'll start by taking a look at the tree context, which is the way the clients invoke methods that are used to alter the behavior of the class when the state changes. So here we have the tree context class. It has its expr method, and this method, of course, is expected to be called after the format method has been called. If you call expr before format, you're going to get an error, and I'll talk about that shortly. And what happens here is when expr gets called, it's going to go ahead and delegate to the underlying state object. And you can see how that works. It says state underscore dot expr this, which is the tree context expression. So it forwards the expression and then delegates itself to the tree context. Now, if you happen to make a call on expr when the object itself, when the whole state tree context object is in the uninitialized state, then of course that's going to throw an exception because it's invalid to call expr until or unless you first called format. So you have to call the format method first, and then you can call expr. If you call expr first, you're in the uninitialized state. So as a result, you're going to get this exception we see here. Conversely, if you've gone ahead and called the format command and said what state you want to be in, at that point, you'll be in the appropriate order uninitialized state. Let's just say for sake of argument that we did format to be in order. So if you say format in order, then what happens is you'll be in the in order uninitialized state, waiting to get an expression to become the in order initialized state. And when that happens, or to make that happen, when the expr method is called when you're in the in order uninitialized state, this code gets run as opposed to this code. And when the code down here gets run, as you can see, it goes ahead and calls the interpreter, passing in the expression, and that will go ahead and interpret the input based on the order that you're doing. So it would be, in this case, in order. And then after we've created the expression tree, we set the expression tree, and then we set the state of the context, of the tree context, to be in order initialized state, because we've now just transitioned from the previous state, which was the state where we were in the in order uninitialized state, to the in order initialized state. And this is one of the reasons why the context is delegated to all the methods that are defined in the state portion, in the state hierarchy, because it's easy to reach back up into the context and say, hey, context, please change my state to new in order initialized state. And then at that point, you could then call the commands like print and eval and so on, and they would all do sensible things. So now that we've walked through the implementation of the state pattern in C++ at a fairly high level, let's go ahead and take a look at the source code to get a really good understanding of how it works in practice. We'll start by taking a look at the tree context class. This is the interface that's provided to the rest of the program. So when users type in requests like format, expr, print, eval, and so on, those things get translated by the command pattern and the command pattern subclasses like format command and print command and so on into invocations to the corresponding method in the tree context. So you can see here that we've got the key methods that are commands like format and expr, print, evaluate, and so on. We've also got setter getter methods to get the current state and set the current state, as well as to get the current tree and set the current tree. And we also keep our interpreter context squirreled away here, which is used by the interpreter pattern we talked about in another video. The actual implementation of this basically uses a unique pointer to point to the current state in the tree context. And we use a unique pointer so that memory management is simplified and it knows how to reset itself and clean itself up when the state transitions occur. And then you can also see that we keep an instance of the expression tree, which is what the user's commands are operating upon when they make those operation calls. Here's the implementation of tree context itself. You can see it starts the world in motion by setting the state field to the uninitialized state. That's the beginning of everything. And then all of its various methods, format, expr, print, and evaluate, they all do the delegation technique that we talked about before. So it says current state, call format, passing the tree context in by delegation, and then pass in the format or the expression and so on. And when we take a look at the state hierarchy in a second, you'll see what those delegated commands actually do. And because we pass in the tree context, then those commands that are being delegated to can reference back to the tree context to do things like set the new state. And that way, when the next call comes through, the state's been set properly here in the tree context. So speaking of state, let's go ahead and take a look at the state implementation. This is, again, the class hierarchy rooted in a base class, an abstract base class called state. As you can see here, it actually is not strictly abstract because all of its methods do something, although what they typically do is they throw exceptions if they're called because you're not supposed to make invocations until you've done the proper sequence of commands. And when you do call something and you're in the wrong state, you get an invalid state exception. So here's the format command and the expr command, the print command. You can see that those have more or less the same signature as the corresponding methods in the tree context, with the difference being that they are passed the tree context ref by using the delegation mechanism we've been talking about. If you come down here, you see that from state, we then have the different concrete states like uninitialized state and so on. Uninitialized state really only has one operation that can be called, which is to set the format to be pre-order, post-order, level order, and so on. So that's the only method that's defined here. All the other methods are inherited from state, and if you call them, as we'll see in a moment, they end up throwing exceptions. So the only thing you can validly call when you're in the uninitialized state is the format method. Everything else throws an exception. We also have something called the uninitialized state factory, which is used to create the appropriate initialized, these appropriate order uninitialized state method and mechanism. You'll see how that works when we get down a little bit further. It's got a method, a factory method called make uninitialized state that leverages these other methods which are used in the context of our wonderful little pattern we keep using for factory methods, where we end up having a map that maps strings to pointers to member functions. And I'll show you that in just a second. So we have this thing called uninitialized state map that will be pre-initialized in order to be able to do the lookups very quickly. Now we have the different uninitialized state and initialized state pairings, for example, pre-order uninitialized state, pre-order initialized state. And these are all the same, just the only thing that differs is what the format is, whether it be pre-order, post-order, level order, in order, and so on. So if we're in the pre-order uninitialized state, the operations we can do there are, of course, set a new format, which we inherit from uninitialized state, and we can also call expr. If we try to call print or evaluate, that's going to end up calling the methods that are defined in the base class, which, as we'll see, will throw an exception. So that's what the pre-order uninitialized state does. Then you can see that once you do that, you will transition into the pre-order initialized state, and there you have a wider range of things you can do. You can also call print, you can call evaluate, you could call expr again to give it a new expression, you could call format again to give it a new format string. So this gives you the widest range of things you can do. And then underneath this, we just have the post-order versions of these things, the in-order versions of these things, the level order versions of these things. This really becomes kind of paint by numbers. Because we are using the pattern, and the pattern is highly structured, everything gets handled in the same canonical way for the different kinds of format ways we can do the formatting. All right, let's go now take a look at the implementation of all this stuff. So there's a couple of helper methods called print tree and called evaluate tree that are called by a number of the other parts of the program. These are kind of fun because they demonstrate many other patterns that we've been talking about. So print tree, as you can see, takes an expression tree and a traversal order and an output stream, and it goes ahead and traverses through the tree in whatever order you asked it to, in order, post order, level order, and so on. And for every element it finds as it iterates through the tree, it says, hey, element, please accept the print visitor. And that then goes ahead and prints out the contents of that particular node in the tree. So this is just basically the visitor pattern, the iterator pattern, the factory method pattern, the bridge pattern. All these other patterns are being applied here in the context of the state pattern, which is setting the wheels in motion. I have a couple different implementations, one of which uses sort of a for loop approach with an iterator, and the other uses the for each algorithm with a lambda function. They work exactly the same way, just showing you can do the same thing in two different ways in C++. Here's the evaluate tree method. This is very similar to print. The only difference is rather than having a print visitor, which we have up here, instead we have an evaluation visitor. And once again, just for kicks, I use the for each method this time, and we go through and we accept for every node in the tree, we go ahead and accept the evaluation visitor, which will evaluate the yield of the tree, and then we will print that here as the total of the evaluation visitor. So those are just some helper methods. We'll see where they get called in a second. Now let's take a look at some of the other methods here. You can see that all the methods defined on the state base class, like format, expr, print, evaluate, those things all just throw invalid state. So you're not supposed to be making any calls when you're uninitialized. So the default is to throw exceptions. We then have our uninitialized state factory, which uses the common trick of making a map, and the map will then be initialized for every type of input order, like in order, pre-order, post-order, and so on. We will go ahead and associate with that key in the map the corresponding value, which is the pointer to member function that knows how to make us the uninitialized state object for that particular format. And this is a very common trick. You can see what we do here is make level uninitialized state, level order uninitialized state, makes a new level order uninitialized state object. Same thing for in order, same thing for pre-order, same thing for post-order. And then the make uninitialized state method looks up in the map, gets back an iterator, assuming it found something that was in the map, it goes ahead and invokes that pointer to member function to make the corresponding order uninitialized state object. Here's what happens in the format implementation for the uninitialized state. Remember, that's the only valid command that you can make when you're in that state. And what it does is it uses the make uninitialized state factory method to make us the correct state, which would be in order uninitialized state, pre-order uninitialized state, and so on, based on the format string. There's some other examples we have here. Let's say we're in post-order uninitialized state. We've been initialized, so we're now the post-order initialized state. When the expr method is called in that state, that will go ahead and make a new post-order interpreter based on the interpreter pattern implementation we talked about before. And then we'll go ahead and say, interpret this expression, which of course is intended to be in post-order. And we use the interpreter to make ourselves a tree that gets stored into the tree context, which as you can see was delegated here quite nicely. And then we set the new state for the tree context to be the post-order initialized state. So at this point, we've now got things ready so that if somebody calls print or evaluate when we're in this state, in the post-order initialized state, then you can see what print does is it goes ahead and calls that print tree method we looked at way up here. And it goes ahead and calls it and passes in the tree, passes in the format string, and passes in cout to write the output somewhere. Likewise, if we do evaluate tree, then it calls, if we do the evaluate method, we go ahead and evaluate the contents of the tree, which prints the yield. And you can see that this only makes sense when we're in the right state. So if you're not in the right state, you don't get these methods called. Similar things happen for the in order equivalents. We have in order uninitialized state expr, which uses the in order interpreter in order to interpret the input expression in order format. And then that sets it into in order initialized state. And then once again, we have print and evaluate that will do the right thing in those states. So hopefully that gives you a much better understanding of how the state pattern can actually be implemented in practice. Again, it's really not that complicated of a pattern, and the implementation is very straightforward. But of course, the level of complexity all depends on the state machine that you're trying to represent in your program. And if the state machine is complicated, then you have a lot more subclasses. If your state machine is simple, you have very few subclasses. This particular example isn't very complicated, but even there you can get kind of lost in a sea of subclasses without understanding the bigger picture view of what the pattern is trying to provide you.